Okay, let us see SRAM and DRAM operations. Firstly, we know that before studying what is meant by SRAM, we should be in a position to understand what is meant by RAM. We all know that RAM is nothing else but it's a random access memory where it is mainly used with respect to or defined with respect to some memory arrays where you'll be accessing some individual bits. So in those cases, we'll be mostly using the RAM operation. And referring to the RAM, we know that RAM is nothing else but it's a random access memory. It means that it has got both kind of operations or capabilities, like it can read and also write the data. So that's the main functionality of a RAM. So it can read and write the data. And coming to the ROM, it's only a read-only memory, which means that it has got only the capability of reading the data, where it cannot directly write the data into the memory elements. It cannot write the data. So that's the main difference between RAM and ROM. So coming to apart from this RAM and ROM, we might have in the lower sections you have studied about what is meant by volatility and also non-volatility. When it comes to the volatility, it means that if a power is turned off, if a power has been removed, then definitely if it is a volatile memory, it will be losing the data over the time. It means that if a power is turned off, it doesn't have a capability of retaining the data. It will not be storing the data, or it will not be uh, making the data to be visible. So that's the main feature of volatile memory. When a power is off, you cannot retain the data. But when it comes to the non-volatile memory, here the data is being stored even the power is turned off. So that's the difference between volatile and non-volatile memories. In the volatile, power is off means data is gone. In the non-volatile, even though the power is turned off or if it is removed, the data can be fetched and it can be used. So among these two, RAM and ROM, RAM is a volatile memory and ROM is a non-volatile memory. Coming to the static and non-static and dynamic memories. So RAM is of two types basically. The first one is called as an SRAM, which is nothing else but static RAM, and second one is called as a dynamic RAM, which is DRAM. So static means whenever the power is applied, the data has been held. Data has been held as long as it has been applied. But coming to the dynamic means here always you are supposed to be refresh the memory element has to be refreshed periodically. So that's why the name has come as dynamic. So here the refreshing of the memory element will be done periodically. Because of that refreshing of memory element periodically, we call this kind of memory element as a dynamic RAM. But whereas in the static RAM, the data can be held in a particular memory element as long as the power is turned on. So these are the major difference between what is meant by static RAM and dynamic RAM. So now first, let us see the operation of a static RAM. Here the static RAM, just now we have studied that it is a static random access memory where it holds the data as long as the power is applied. Since it holds the data as long as power is applied means once the power is turned off, it don't have any kind of capability of holding the data or retaining the data. So that's why this kind of SRAM is called as an volatile memory. It's a more volatile memory. And coming to the operation of this SRAM, the operation of SRAM has got three major operations. The first one is called as an hold operation, second one is called as an write operation, and the third one is called as an read operation. You can see over here the figure which is shown here in the PPT. It is an 60 SRAM cell. It means that it has got 6 different transistors. 6T, T stands for the transistors. So now here this is MAL and MAR. These are the access transistors which we have just named in order to differentiate these two transistors. MAL and MAR are the access transistors, and this is an inverter. It's an inverter NOT gate and another NOT gate. So we know that if I need to design an NOT gate with the help of CMOS circuit, CMOS logic, then definitely I need two different transistors. So it means that this NOT gate has got two transistors, and even this this NOT gate has got two transistors. So ultimately, we are having in this particular figure 6 different transistors. So we call it as an 6T RAM cell. It's called an 6T SRAM cell. So now coming to this particular part, This particular part is called as a latch. It acts as a latch. It means that it is storing, it is an storage element. You might have studied in your digital electronics regarding what is meant by latch and what is meant by flip-flops. So now here, this particular one is acting as a latch. Why I call it as a latch? Because here, once if a data is stored here, assume that if I have given 0 over here for the first one, if I have given a 0 as an input at the first inverter, if I have given a 0 as an input at the first inverter, the output of the first inverter will be 1, and again the same output of the first NOT gate or else our CMOS inverter will become as an input to the second NOT gate, and it will be producing again an output of 0. So ultimately what is happening here?
Class
Please kindly mute your devices. So ultimately what is happening here? Ultimately a data is being locked up. A data has been locked up over here in this particular closed element. So that's why since a data is latched in this particular memory element, we call it as an, this kind of memory element is called as a latch element. So now here this particular setup is called as a latch, and here this is how a data is logged over here or latched in this particular uh, closed network. So see now, first of all, the description about this particular figure. In this one, you are having 6 transistor. It's an SRAM cell, 60 SRAM cell, where this there are two inverters which are cross coupled. It's a bistable inverters are there which are cross coupled for the storage of the element. This is how the storage takes place. Just now I explained how a storage or the element is or a bit is been locked up or stored here. And MAL and MAR nothing else but the access transistors, which whose gates are connected to the word line. WL means word line, and here bit and bit bar is nothing else but it is the line through which you will be writing the data into this memory element, or else it is a line through which you will be reading the data from the memory element. So bit and bit bar are the access lines where you will be able to fetch the data from the memory element, or else you will be able to uh, you'll be able to write the data into the memory element. So how to write the data into memory element? Okay, anyway we can read the data and data will be obtained over here, but in order to write the data, you're supposed to apply some amount of voltage over here to the bit and bit bar, so that that voltage will be stored in this particular latch, depending upon the on and off nature of these two access transistors. Whenever these two access transistors are on, then only a path has been created between this latch and this particular bit line. So we can easily we can write that particular data into this one. Why? Because we know that a voltage potential flows from high potential area to the low potential area. If there is no if there is a low potential area over here and it's a high potential area, then definitely we can write the data from the bit line into this particular latch. So now let us see how this operates. Whenever the bit line, whenever the word line is 0, whenever the word line is 0, what happens? If you are inputting the word line equal to 0, the same 0 logic 0 is given as an input to the gate of these two transistors. If the gate of these two transistors are logic 0, we know that since these are the N type of transistors, N type of transistors will be turned off. It means that whenever the N type of transistors are turned off, you will not be having any connection between this latch and this bit line. It means that your data is held in this latch. So that's why WL equal to 0, whenever the word line equal to 0, the hold operation will be taking place. So now that's how the first operation goes on. That's a hold operation goes on whenever the WL equal to 0. These two transistors, NMOS transistors, will be turned off. Because of that one, the connectivity between the bit line and the latch will be lost, and because of that connectivity has lost, now the data is held in this particular latch. So this is called as an hold operation. Now coming to the WL equal to 1. Whenever the WL equal to 1, if the word line equal to 1, then definitely these two transistors will be turned on. If the two transistors are turned on, we know that there's a path has been created between the bit line and the this particular latch. Because of that one, the data can be easily read, or else it can be written into this particular latch. So that's why we can write it here as WL equal to 1. read or write operation takes place in this particular SRAM cell. So now in the next slides, we'll see in detail about how it happens.
Sir, what is the full form of MAL and MAR, sir?
It's just the name we have given for the MAL for the access transistors. It's a name MAL. Mostly in the other particular textbooks, you'll be seeing it as only the access transistors. Don't get don't think much about MAL and MAR. It's only the access transistors.
Okay, sir.
MOSFET access transistors.
Okay.
Okay, now let us see now here. Yeah, SRAM operation. In this SRAM operation, first, as we have discussed up to now, hold operation. What happens in the hold operation? Whenever the WL equal to 0, whenever the word line, WL means word line is equal to 0, the access transistors are off. Since these two access transistors are off, what happens? The data which is stored here in the latch will be held in this particular latch. Why? Because it has got no provision to move out of this latch, because there is no connectivity. The path is not there. If you don't have any kind of path to move from this particular latch to the word line, or sorry, to the bit line, you cannot expect the data to move out of this particular latch. So that's how the hold operation takes place. Coming to this write operation, whenever the WL equal to 1, if a WL equal to 1, you can see these are the write and read operations over here. So whenever the WL equal to 1, both the access transistors are turned on. Whenever the access transistors are turned on, now you see we are writing the data. A new data is applied to the bit line. Means you're applying a new data means what? We know that our data can be applied either in case of logic 1 or in case of logic 0. So how to do that one? We'll be doing that one with the help of applying a voltage to the bit line. Voltage to bit line means what? If you applied here voltage VDD, it means it will be taking it as an logic 1. If it is logic 1, it's a bit bar here. Bit bar means it will be logic 0. So that's how you will be applying the complementary inputs over here. So when you apply this voltage to this bit line, then since a path has been created, this particular data which is VDD, which will be much greater than the what are the data is stored over here. So the potential is greater on the bit line than in the latch. So now the transferring of data takes place here. You can see here this something like yellow or orange kind of color, which shows this arrow mark, the writing of the data into the latch. So this is how the writing of data takes place. So now the old data will be overwritten, or it will be overridden by the new data. So this is how the new value is stored in this particular memory element. So coming to the read operation. So in the read operation, we are supposed to study about another circuit, which is called as a sense amplifier. What is meant by sense amplifier? Sense amplifier is nothing else but it's a differential amplifier. You might have studied in your digital electronic circuits in a digital electronic course. In that particular differential amplifier, you'll be having two different inputs are to be given to a differential amplifier. Depending upon the two different inputs, it will be producing the output of the particular two different inputs. So that's a general operation of a differential amplifier. So now here the differential inputs, the input of the differential amplifier will be connected to bit 1, and again another complementary input will be connected to the bit bar. Another complementary input will be connected to the bit bar. So now that's how the differential input will be given to the sense amplifier. Depending upon the sense amplifier, it will try to read the data. So see now how it goes on. If word line equal to 1, whenever the word line equal to 1, the bit and bit bar will be read by the difference amplifier. So now you will be reading the data with the help of difference amplifier. Since it is connected to a difference amplifier, the difference amplifier will be working and it will be reading the data. So let us see what happens in this differential amplifier. Here the sense amplifier is nothing else but it is a simple differential amplifier where comparing of these two data will be taking place. Comparing of this two data. Why? Because we will be getting two data, two bit line operations, that is bit and bit bar operation. If the bit is much greater than the bit bar, then we can say that the output of which is stored over here, the output which is stored in this particular sense, in this latch will be equal to 1, logic 1. If the bit bar is greater than bit, then we can say that the output which is stored or the data which is stored in the latch will be equal to 0. So that is how the sense amplifier will be helping us in order to read the data from which is stored in this particular latch of an SRAM cell. So now it always helps us to find out the outputs which is stored in the particular latch with the help of sense amplifier. So this is a simple operation of an SRAM cell, and you can make it clear that this is very important concept as per your university question paper is considered. So now let us see now another variations of SRAM cells. So see now in the previous one, in this particular diagram, we have drawn a diagram with the help of NOT gates. So now we are trying to completely draw this diagram in terms of CMOS circuits, in terms of CMOS logic. So now if that is the case, so now this 60 cell will become as a CMOS circuit where you have used a cross-coupled inverters. The cross-coupled inverters have been used over here. PMOS and NMOS will make us one NOT gate. Again, one PMOS and NMOS will make us another NOT gate. So this is a complete 60 SRAM CMOS SRAM. And compared to the, and another kind of structure is also shown over here, which is a 40 SRAM cell, which has been designed with the help of active load transistors. You can see this is nothing else but it's an load active load transistor cell, where it is again it's nothing else but it's an inverter only. Instead of using the PMOS, you'll be using one resistor. Active load is being used in case of PMOS. So now this becomes as an active load inverter. With the help of two active load inverters, we have drawn this particular SRAM cell. Among these two 60 and 40 cell, 60 is much more used than compared to the 40, because the major advantages of 60 cell is that it is very it is having a better noise immunity. It means that the noise characteristics, whenever you try to draw the waveforms, you'll not be finding out much amount of noises in the waveform, or glitches will not be there. It is having very much noise immunity, and also it is very much less power consumed circuit. But whenever it comes to the 40 cell, it's a power consumption circuit. Why? Because since you are having an resistors over here, the resistors will be very huge. It will be of almost 1 giga ohm values. If it is such a huge resistors have been used, then definitely you can think that if I need to draw the layout of an SRAM cell, then since I'm using a resistor over here, then definitely it acquires, or it requires a larger amount of space on the IC chip. So that's a major disadvantage of the 40 SRAM cell. And coming to the power consumption, assume that here at this particular node, if I'm having 0 over here, I'm having a 0. Since the another terminal of the resistor is connected to VDD, what happens? Since there is a difference in voltage at this node, and this node, then definitely the potential difference has been created. Due to that, again, the potential gradient takes place, and because of that one, there will be a power dissipation will be there. The power dissipation, loss of charges takes place, and the power dissipation will be that's how the power dissipation takes place over here. So that's why this particular 40 cell is called as an high power dissipation circuit, whereas coming to this one, it's a low power dissipation circuit. And another disadvantage of a 40 cell is that it requires more amount of space in order to draw the layout on the and it also acquires more space in order to construct any kind of IC for this SRAM cell. So these are the differences between 60 SRAM cell and also 40 SRAM cell. And let us see the critical design. This is a not much useful as a part of your B.Tech course, but anyway, it will be very much helpful to you to understand in detail how to construct or how to design a very optimized SRAM cell. In order to get an optimized SRAM cell, first you should be in a position to make sure that all the transistors are having the minimum WL ratios. It means the aspect ratio should be very less. The size of the transistors should be very optimized, such a way that it will be consuming more it will be consuming less amount of power. So that thing you should be taken care. It should use the minimum sized transistors in order to save the area. That's the most one. If you can do that one, if you are designing an optimized cell, then definitely your design will be a robust one. Robust design can be occurred. And apart from that one, if you come to this resistive model of this particular cell, you can see here now this both RA and RN. These are the transistors where it has been drawn in terms of a resistive model. You might have studied in your digital or analog electronic course how to draw the large signal model and also small signal model of amplifiers. So this we are trying to draw a resistive model of this one. Even in the large signal, in the small signal model, you'll be indicating all the design in terms of resistors and also capacitors. So that's how the small signal and large signal model designs will be done. So here, if you come to this one here, we want the larger values of these two resistors than the value of this RA resistor. Then only if this has been done, why we are doing, because RP and RA can have a voltage drop. In order to overcome that voltage drop, we need this particular RN and RP to have larger values. So that's the meaning of this particular RA will be much smaller compared to the RP and RN, which will indicate this is nothing else but it is an indication of CMOS inverter, where RP is nothing else but it is a pull-up transistor, which is a resistive model for the pull-up transistor, and RN is a resistive model of the pull-down transistor. And this is a VDD which is connected to the CMOS, and this is a ground which is connected to the NMOS. And also the RN should be always much greater, 2 times greater than the RA value. So these are the some design considerations in order to design an optimized value of a particular SRAM cell in order to be a robust kind of a design. In order to get a robust design, you are supposed to optimize all these values. Your W by L ratio should be W by L ratios are to be set, and also this you should take care about the resistances which come over here in this design. So that's how you can make it up. And
Sure.
DFF is nothing else but here I have written in terms of D flip-flops. In the D flip-flops, what happens? The overriding of data takes place. If you know that operation of flip-flops, you can understand this one. Unlike in the D flip-flops, where only one inverter over here used here, which will be override the other inverter. So this is
Sir.
simple operation.
Sir,
Yeah, please tell me.
sir, once explain the resistor model, sir.
See, in this resistor model, if you see this one, always you should make clear that your RP and RN should be much greater than the RA value. Why you're supposed to make clear that RP and RN should be much greater than RA value? Because this is acting as a complete CMOS inverter. This part, I'm talking about this one. It is acting as a complete CMOS inverter. This is a main part. Why I call it as a main part? Because of this structure only, your data has been held, or else your data is read or your data is stored. So now you are supposed to make clear that RA and RP should be much larger than this access transistor, which is nothing else but this one. This RA will act as in this particular transistor, access transistor, and this is again another access transistor. So
Why will use the access transistor, sir? What is the use of RA?
RA is a resistive representation of an access transistor.
Yeah, sir. What operation will it do?
What is the operation of an access transistor in the SRAM cell? How does an access transistor helps?
Like
Just now I explained in the previous slides.
enable.
What enable? It either makes a path between the bit line and the latch, or else it will disconnect a path between the bit line and latch. Whenever it is disconnected a path between the bit line and latch, the data will be held. Whenever a path has been created between a bit line and a latch, then
Read on,
data
write
has been read or write operation. The same thing happens here. We are just trying to represent the entire SRAM cell in a resistive model. That's only the difference. Entire operation will be same. Is it clear?
Yes, sir.
Okay. So now this is how you design the resistive model in order to get an optimized design of an SRAM cell. So now here you can see this is a layout of this SRAM cell. You can see the different layers have been used over here: metal 1, metal 2, and again poly connections. So this is how the layout looks for the SRAM cell. Now coming to multi-port SRAM cell. Multi-port means In this multi-port, we are trying to use a 2-bit line. 2 word lines have been used, and again 2-bit lines have been used, where you can access more amount of data, or where you can write more amount of data. So only for in order to show you how the multi-port, in the previous case, it was only one kind of data has been fed and one kind of data has been acquired. But here in this one, we are trying to write, read, and hold multi-level of bits in a particular SRAM cell. So this is how the diagram looks for this multi-port SRAM cell. The applications where we can use this one, this SRAM cells have been used as register files, cache, and also it can be used in a network switch, and also ASICs, application specific integrated circuit. ASIC means application specific integrated circuit. So now cache. In the previous lectures, I have told that if you are trying to design a microprocessor, where you're having a, let me take an example of 2-core microprocessor, you'll be having the 2 CPUs in that one. If that is the case, then the more than 50% of that particular 2-core microprocessor, you can just look at the diagram of that one in a textbooks. If you can find the 2-core microprocessor diagrams, the almost 50% will be with CPUs, and the next 50% will be with cache. So now here this cache is nothing else but it is a SRAM cell. That's the importance of SRAM, which is given in order to design any kind of microprocessor. So almost more than 50% of your microprocessor will be designed with the help of SRAM cells. So this is how the multi-port SRAM cell can be, the schematic can be designed with the help of 2 access transistors, 2 bit lines, and 1 selection line, and 1 address decoders. So this is for SRAM. And coming to the anyway, I have explained about sense amplifier. This one particular slide I have kept for sense amplifier. I hope you remember the diagram of your differential amplifier. So this is a differential amplifier, where D is nothing else but this is the input which is given to the bit line of SRAM, and D bar is nothing else but this is the input which is given to the bit bar of an SRAM cell. So now this is a we call it as a mirror circuit. In the analog electronics, if you have studied, you will be understanding this one. Mirror is been done between these two. The cross connection between the gate of a first PMOS is connected to the this one drain of another first PMOS. So this is how the differential amplifier looks, and you can see that we have studied in that SRAM cell that whenever the bit is much greater than bit bar, then definitely what happens, our output will be logic 1. If the bit is lesser than the bit bar, then the output will be very low. So this is how your SRAM cell will be used in order to understand what is meant by this is the differential amplifier, how you can understand the read and write operation takes place in the SRAM with the help of sense amplifiers. So this is the concept regarding SRAM cell. Now let us enter into the DRAM. DRAM basics. First, DRAM means what? We know that it's a dynamic access memory with respect to the its dynamic nature. Here, dynamic nature means it has to be periodically, it has to be refreshed every time. Because it has been refreshed every time, we call it is a dynamic nature RAM. Here in this particular DRAM, if I consider 1T DRAM, you can see that you'll be having one bit line over here, and this is a word line WL. You'll be having only one transistor, which is N transistor is there, which will act as an access transistor. And to this N transistor, one terminal is connected to the capacitor. The voltage across this capacitor is called as Vs, and the power line, which is given, the ground terminal, will be given to another terminal of a particular capacitor. So this is the capacitor which will be very much useful in order to hold the data, or in order to read and write the data. So in this 1T DRAM cell, this capacitor plays a very important role. So that's why we call it a storage element. This is called as a storage capacitor. So see now the comparison between the SRAM. DRAM is smaller and less expensive per bit. It is having less number of transistors, so it will be less expensive. And it's also, since in the SRAM we have used either 4 transistors or else we have used 6 transistors. But when it comes to the DRAM, we are using only 1 transistor. So it's a very smaller in size, and also it is less expensive. And compared to that SRAM, Since here in the DRAM, every time it has to be dynamically, it has to be refreshed. So that's why periodically the refreshing takes place over here. So it's not that so faster than compared to the SRAM. So SRAM is faster, and in the DRAM it requires more peripheral circuits will be there in order to construct the DRAM. Many kind of capacitive elements will be used, capacitors will be used. So that's why it requires more number of peripheral circuitry. Coming to its nature over here, it's a volatile kind of RAM which loses data when the power is removed. So now the diagram of this one, which will be having one NFET, and again one storage capacitor, one word line, control line will be there, word line, and again one data input will be given, that is given to the bit line. So whenever if you're feeding it data, it means that you're supplying some voltage to this bit line. And again the read and write operation will be done with the help of if you want to read the data, the reading of data will be done with the help of again the sense amplifiers only. You'll be the sense amplifier input will be connected to the bit line, and the differential amplifier will read the data. Depending upon that data, we can say what kind of data is stored over here in this capacitor. So see now, let us see the operation of DRAM. In the DRAM here, the RAM data is held on the storage capacitor. So now it's a temporary leakage takes place. Temporary leakage means what? Here, if a data is held over here, since it will be having a higher potential than compared to the ground. If there is a higher potential than compared to the ground means what? Definitely the potential leakage takes place, or from high potential area to the low potential area. Ground is at low potential. The data which is stored in the capacitor will be much greater than the ground. That is nothing else but zero potential. So ultimately the leakage of data takes place. So there will be it's a temporary holding of data takes place here, which means that because of the leakage currents which drains the charges, the draining of charge takes place from the capacitor due to this potential difference which occurs over here between the two terminals of a capacitor. So now let us see the storage of data. This is a basic about storage of data. Here simply I have given about what is meant by storage of data. We know that if CS is charged to VSS, then definitely the storing, how does the charge will be stored over here? We know the basic formula of capacitor, Q equal to CV. Q equal to CV is a basic capacitor formula, or else we can write it as C equal to Q over V. That's a definition of a capacitor. The amount of charge stored in a particular capacitor is given by C equal to Q over V. So Q equal to C into Vs. Whenever the Vs equal to 0, then definitely this product becomes 0. So ultimately the Q is also 0. Whenever the Q is equal to charge in this capacitor 0, so ultimately we can say that the logic 0 is stored in this particular DRAM cell. Or else if Vs is larger, means something, assume that it is VDD. If a VDD is given as Vs, then definitely this product becomes much larger. Then we can say that the QS is greater than 0 and logic 1 is stored in this particular DRAM. So that is how the operation of a 1T DRAM takes place over here. So let us see the write operation. Initially, write operation, the write operation or read operation mostly happens on WL equal to 1, and the hold operation takes place at WL equal to 0. So first let us see the write operations over here. Whenever the WL equal to 1, if WL, the word line equal to 1, the access transistors will be turned on. Oh, sorry, here it's only one access transistor. The access transistor is turned on. If that is the case, then the we are supposed to apply some voltage to this particular bit line. You can see here now the VDD is applied, or some voltage VD is applied here. It can be high voltage or else it can be low voltage. Depending upon the voltage which you apply over here, that particular voltage will be stored in the capacitor. So now if you apply a voltage to this particular bit line, then CS is charged. Depending upon this one, see now, if you apply some voltage here, since here a leakage of data is taking place, leakage of charge is taking place, definitely we can say that this particular node will be much greater than compared to the charge which is stored in the capacitor. So now again a potential difference is created between these two terminals, this particular node and this node. Then because of that difference in the potential, a path is already created because of WL equal to 1, the transistor is turned on. The potential will move from this particular bit line to the capacitor, and that's how the writing of the data takes place in this 1T DRAM cell. A data is charged Whenever you apply the low voltage, then definitely what happens, again a potential difference is created here. If this is logic 0, if a low voltage means consider it's logic 0, but here there is some charge which is much greater than this one. In that case, what happens, the charge will be leaking, the charge will discharge from this one, from the capacitor to this bit line, to the bit line. So that's how we call it as a discharging of data takes place from the capacitor. So this is how the write operation will be done, or the read operation will be done. So you can see now, whenever the VDD equal to 0, sorry, whenever the VD equal to 0, what happens? The QS is equal to 0, the logic 0 is stored over here. Logic 0 is stored in this capacitor. Whenever the VD is equal to VDD, then what happens? The Q will is become 0. The Q is much greater than this one. It means that since there is a transistor over here, if a VD is equal to VDD, we cannot tell that the entire VDD, the high voltage is stored in the capacitor, because there is some threshold voltage is there. We are supposed to remove that threshold voltage. We should subtract that one. Only that amount of voltage can be stored in the capacitor. So it will be VDD minus VTN will be that amount of voltage will be stored in the capacitor. So that's why we have written Vs equal to VDD minus VTN. Then ultimately the formula for charge is equal to C into V. So it is C into VDD minus, sorry, it's equality has come here, VDD minus VTN. So that's why we can say if some data is stored over here, we call it as a logic 1 is stored. In the hold operation, you all already whenever the W equal to 0, the path has been disconnected between the bit line and the capacitor. If there is a path disconnection, whatever the previous data is stored in the capacitor, that will be held over here for some amount of time. Why? Because discharging again takes place between these two nodes. The potential difference will be created and the discharging takes place. So that's why we can say that the hold operation, the data is held temporarily, means because you cannot expect the full amount of data. Because of that reason, we are always supposed to refresh this one in order to get the actual value of data which is stored over here. So that's how the hold and the write operation takes place here. So this is regarding the some particular refresh operation I have given here, how the refresh operation takes place. In the refresh rate, in order to hold the data as long as power is applied, the data must be always refreshed. Why the data is always refreshed? Because there is some amount of leakage of current or a charge takes place from the capacitor because of the ground terminal which is connected to the capacitor. So due to that reason, you are supposed to always refresh the data. Since it is refreshing every time, we call this kind of cell as memory cell as an DRAM cell. Again, the refreshing rate you can see here. The refreshing rate can be the frequency at which a cell must be refreshed in order to maintain the data. It is 1/2 the time of this particular second time. You should always refresh at this rate. If you can refresh at this rate, if the frequency is at this rate, then only you can hold the data, or else entire data will be discharged to the ground. So that's how the refresh takes place. So this is the some flowchart I have given regarding how the refresh takes place. And this is regarding a DRAM cell using a one kind of capacitor, trench capacitors, which is used in designing the layouts. This is a trench capacitor. There are two kinds of capacitors we can use here in order to design the layouts. First kind is called as a trench capacitor, where a junction cap is being used. This kind of design we call as a trench capacitor. So here, junction capacitor will be used with a large junction area. This area will be large. So because of this one, since it looks like a trench kind of form is formed over here, we call it a trench capacitor. And apart from that, we can use again stacked capacitors also can be used with the help of polyplate capacitors. We can use this. We can design the layout. And typically you can see now the minimum size or the area of 1T DRAM cell, it is typically only 30% of the chip is needed in order to refresh this particular data. So 30% of the chip can be used for designing any kind of 1T DRAM cell. For DRAM in CMOS, must minimum area of the capacitor. It should be having a minimum area in order to design any kind of DRAM in a CMOS logic. That should be approximately like 30%. but the larger capacitor which is greater than 40 femtofarad. It means that if you are trying to use a DRAM, or if you're trying to design a DRAM with the help of larger capacitor, that capacitance value should be greater than 40 femtofarad, which is very much accessible in order to increase the hold time. You can increase the hold time so that you can, whenever a data is held, then only you can tell what amount of data is stored in this particular capacitor. So the minimum value of a capacitor should be 40 femto value. So this is regarding what is meant by DRAM.